Welcome to the next lecture on mobile radio propagation. Today we will talk about certain channel parameters. Let us first look at the outline of today's talk. We will summarize what we learnt last time. Then we will proceed with certain time dispersion parameters, which are mean excess delay, RMS or the root mean square delay spread, and the maximum excess delay over XdB. We will then learn about coherence bandwidth, an important channel characteristic. It is useful also for fading countermeasure. We will look at coherence time and how to determine coherence time for standard channels. First, let us start with a brief recap. Last lecture dealt with small scale multipath measurement. We then discussed about various channel sounding techniques, which were direct RF pulsed systems, spread spectrum sliding correlator channel sounding technique, and frequency domain channel sounding. We took the example of ultra wideband or UWB measurement, and we first talked about the existing channel models for UWB. Then we discussed certain channel measurement campaigns that have already been carried out by different companies and universities. We talked about time domain and frequency domain measurements, and we found the equivalence of the two techniques, the time domain and the frequency domain measurements. Finally, we discussed the Intel channel measurement campaign as well as the channel measurement campaign for ultra wideband carried out at IIT Delhi. Today, we will learn that a lot of information obtained by doing channel measurements can help us determine channel parameters, which will in turn help us design better wireless systems. So, what are the parameters of a mobile multipath channel? How are they derived? The basic parameters of the mobile multipath channels are essentially derived from the power delay profile. We have spent enough time understanding and learning how to obtain the power delay profile for any wireless channel, be it mobile or stationary. Now, we realized that this power delay profile can be measured either in the time domain or in the frequency domain, and we also establish an equivalence. The important parameters of concern are the time dispersion parameters, the coherence bandwidth, and the Doppler spread of the channel. Having information about these three things, the time dispersion parameters, coherence bandwidth, and the Doppler spread, we can know something about the channel and design our receivers accordingly. Our transmission schemes will also derive information from these things and probably design better systems in order to overcome the effects of fading. Now, a brief look at what the power delay profile is. For small scale fading, the power delay profile of the channel is simply found by taking the spatial average h subscript b t semicolon tau whole squared over a local area. How small? This local area depends whether it is an outdoor measurement campaign or indoor measurement campaign. It can go from 2 meters indoors to 6 meters outdoors. If P of t, which is the pulse being used to sound the channel, has a time duration much smaller than the impulse response of the multipath channel, in that case the received power delay profile in a local area is given by P of tau approximately equal to average value of k, absolute value h subscript b t semicolon tau whole squared. K is the scaling factor. The bar represents the average over a local area and over several snapshots of h, b, t semicolon tau. The gain k relates the transmitter power in the probing pulse p of t to the total received power in a multipath delay profile. Essentially, it is a scale parameter. What we measure in most of the cases is this p of tau. Okay? It is the averaged value that we measure in the oscilloscopes. So, the measurements can be carried out by various channel sounding techniques. Plots of relative received power as a function of excess delay with respect to a fixed time delay reference can be taken out. The power delay profile is found by averaging instantaneous power delay measurements over a local area. Now, typically researchers use lambda by 4, the quarter wavelength, for sampling interval. This is a rule of thumb. What do we mean by a local area? How big is a local area? Well, it is less than 6 meters outdoors. So, suppose I am trying to do channel sounding for GSM scenario or a WCDMA scenario, then I will go outdoors, but my power delay profile would be limited to about 6 meters. The samples will be taken at approximately lambda by 4. However, if I am doing indoor channel measurement, then the power delay profile will be taken over 2 meters only. Again, it is at quarter wavelength sampling intervals. Beyond that, we come into the long term fading, not the small scale fading. Let us look at one example of a typical measured power delay profile. So, here in this figure, we have on one axis the delay in nanoseconds. So, as you can see, it goes from 0, 100, 200 up to 600 nanoseconds of delay. The delay depends on your environment. On the other axis, we have the measurement time in second. It shows that the channel now will be different from after 10 seconds or 100 seconds and so on and so forth. So, the channel is varying with time. We will try to capture both the delay, the inherent nature of the channel, and the time varying nature of the channel by our different measurements of coherence time and coherence bandwidth. On the z axis, we have put the signal strength in dBm. So, if you look at it carefully, if you just go along this axis, then for a particular instant in time, we are taking the channel impulse response measurements. And what we are developing here is a notion of the reflections at close by locations given by this sharp peak here and some further reflections here and here. If we conduct the same experiment after say 100 seconds or 200 seconds, we come up to here. So, the channel has changed, the reflectors have moved. Question?
Floor of the receive power, it's centered around the minus 85 dBm.
Right.
So, is this a noise floor?
The question being asked is regarding the floor of the received power. It appears from the figure that close to minus 80 dBm is what my floor is. What is this figure minus 80 dBm? Does it relate to the noise floor? So, the answer is yes, this apparently represents the noise floor, the average received power obtained between the transmitter and receiver separation kept at certain distance. You keep on receiving about minus 80 dB when you know significant signal is received. The other strong reflected or line of sight components can be obtained which are close to minus 50 dB or minus 70 dB or 60 dB. Okay. This also represents something as the receiver sensitivity that we are dealing with. If my receiver was more sensitive, I can probably get more signals below here also. So, that is kind of a threshold level. Let us look at another example, this time for the outdoor power delay profile. Here is an example of outdoor power delay measurements for a 900 megahertz cellular system. On the x-axis, there is the excess delay in microseconds. Please note, when you carry out power delay measurements outside, the excess delay is of the order of microseconds, whereas inside the room or indoor situations, you are more likely to find excess delay in nanoseconds. On the y-axis, we have put the signal strength in dBm. Clearly, there is a line which is a threshold about the receiver sensitivity. Okay. So, you can see that the power delay profile varies a lot, right, and you can see clearly that there are some clear reflections. Now, on the other hand, if you want to consider an indoor power delay profile measurement, again on the x-axis if you put the excess delay, please note this time you are working in the domain of nanoseconds, whereas on the y-axis you have the normalized received power, you see far many stronger reflections spaced close by. If you go back, you will realize that the reflections were far apart, and there were some strong reflections and some weak reflections. And beyond a certain time, you do not have much reflection, they go down drastically. This is an example for a 4 gigahertz system. Later in today's talk, we will list out certain measurement data obtained for this excess delay both in indoor as well as outdoor environments. It is interesting to note that this excess delay is also a function of the frequency of operation. You will get a completely different profile if you go from 4 gigahertz here to say 10 gigahertz or even to 900 megahertz. So, let us now talk about the time dispersion parameters. The time dispersion parameters grossly quantify the multipath channel. These parameters include first the mean excess delay, the root mean square or RMS delay spread, and of course the maximum excess delay. We will talk about this x dB in the parenthesis in a minute. Now, the mean excess delay tau bar is the first moment of the power delay profile. So, it is almost like the first moment given by the power delay profile measured by an oscilloscope. Mathematically, tau bar is equal to summation over k a k squared tau k divided by summation a k squared. Now, a k represents the path gain for the kth path. If you are actually carrying out the power delay profile measurement, then it is nothing but the power t k. So, if you are actually working from the power delay profile curves, then you are not bothered with the ak, you do not have to square it, you directly get the ak squared divided by summation over k p tau k. Question?
So, what is the meaning of power gain and the path gain? It is k.
The question being asked is, what is meant by a subscript k? Here we are dealing with a multipath channel. So, there are more than one paths from the transmitter to the receiver through reflections, scatterings, diffraction, etc. For any particular path, the signal gets a path gain which is ak. It can be smaller than 1. So, if it is 0.1, it means that for that particular path which I receive through reflections, the receiver strength is 0.1 times what I sent. Whereas, for second path, the path gain might be different. What I could get is a much stronger reflection. It's a better reflecting material, maybe it's a metal, and the path gain for that reflection will be larger. Line of sight will probably have the strongest A sub k. If there are 10 multipaths, then k will start from 0 to 9. There will be 10 multipath components. Okay. Tau k represents the delay associated with that path. If the reflector is located far away, then tau k will be large. If the reflector is close by, tau k will be small. Soon we will look at an example to learn how to calculate this mean excess delay. Please remember, this term mean excess delay will have some correlation with my maximum data rate that I can support in the channel. So these measurements are important in designing our exact communication system. The second important time dispersion parameter is the root mean square RMS delay spread given by sigma subscript tau. Each multipath signal travels through different path lengths. So the time of arrival for each path is different. Clearly, we understand this. A single transmitted pulse will be spread in time when it reaches the signal, when it reaches this receiver. This effect, which spreads out the signal, is called the delay spread. We are trying to characterize, measure and quantify this delay spread. The delay spread leads to an increase in the signal bandwidth perceived at the receiver. So these are some of the effects of the time dispersion. So how do we quantify this sigma subscript tau? What is the physical interpretation of the RMS delay spread? The RMS delay spread actually characterizes the time dispersiveness of the channel. So it is obtained directly from the power delay profile. It indicates the delay during which the power of the received signal is above a certain value. It is the square root of the second central moment of the power delay profile. So mathematically, sigma subscript tau is given by under root tau squared bar, the average value of tau squared, minus tau bar whole squared, which is nothing but the second central moment of the power delay profile. How do we obtain tau squared average? It is given by summation over k multipath channels, A subscript k whole squared, tau k squared, where A subscript k is the path gain of the kth channel and tau subscript k represents the delay associated with the kth channel. Normalized by summation over k A subscript k whole square. If you are working with a digital oscilloscope which averages, we directly get the power delay profile and we do not have to worry about the A k whole squared. We can directly plug in the values of P tau k. Fine. So first you calculate tau squared bar, the average value, and then from that you obtain the sigma subscript t, which is nothing but the root mean square delay spread. Here we have a table of the measured values of the actual RMS delay spread taken indoors and outdoors by various researchers. So if you see, the leftmost column talks about the environment where it is urban, suburban and indoors. There is a whole range of frequency that has been deployed starting from close to 910 megahertz up to 1900 megahertz. Now the RMS delay spread that we were talking about by measurement is found out to be sigma sub t, ranging from 1300 nanosecond average to 600 nanosecond standard deviation and 3500 nanosecond maximum in a dense urban city like New York. Indoors, it is interesting to note that if you look at indoor office building and carry out the same measurement either at 1500 megahertz or 850 megahertz, the root mean square delay spread changes. You have much smaller root mean square delay when you work at 1500 megahertz, whereas if you go at 850 megahertz, much larger wavelengths, your maximum root mean square delay also increases. So that is an interesting effect. So let's talk about the time dispersion parameter maximum excess delay of x dB. It is the time delay during which the multipath energy falls to x dB below the maximum. So I am talking about the strongest signal received. I take a line which is 10 dB if my x is 10 below my maximum received power. In general it is x dB below the maximum, and then find out how many reflections are there within that region. How many strong reflections are obtained till the multipath energy falls to x dB below the maximum received power. So the maximum excess delay is nothing but tau of x minus tau 0. Tau 0 represents the first marker for the received signal. Tau 0 is the first arriving signal, tau x is the maximum delay at which a multipath component is within x dB of the strongest arriving multipath signal. Okay. Please note that the strongest arriving multipath signal necessarily does not mean it is the first one you get. You can have a much stronger reflector and no line of sight, in which case maybe the second or the third reflected signal is the maximum. I compare it with the maximum value, not the first arriving value. So this maximum excess delay defines the temporal extent of the multipath, that is above a particular threshold. Tau of x is called the excess delay spread of a power delay profile. So now let us look at an example from measured data. We have here on the x axis the excess delay in nanoseconds. Clearly these measurement data have been taken in an indoor setting. On the y axis ordinate, we have the normalized received power in dB. What we see is the signal has a large enough delay spread, but we would need to characterize it. So the first thing that we need to do is to find out what is the mean excess delay, which is the tau bar. So here from this measured data we can calculate for this particular sample the mean excess delay comes out to be about 45 nanosecond. Okay. It is nothing but the statistical mean, but that is not the only thing we are interested in. We are interested in also the maximum excess delay. Let us fix our threshold at 10 dB. So if 10 dB is our threshold, then 10 dB is below the largest peak here. Luckily here the first peak is the largest, otherwise we would have to work with a peak which is the largest anywhere in the middle also. So let us put a threshold value at 10 dB. So here is the last received signal which is 10 dB below the maximum received strength. Anything below it does not figure. So I find out the time delay with respect to the maximum, and here this stretch which is close to 84 nanosecond gives me the maximum excess delay for a 10 dB threshold. The other parameter that is important is the root mean square delay spread. For that we have to find out the under root of the tau squared bar minus tau bar squared, okay, and that if you calculate comes out to be about 46.4 nanosecond. Just to illustrate the point, it is root mean square is only so much. This is the actual root mean square spread around the mean. Okay. These three parameters will inherently help us determine how fast we can push in data in the channel without the need for an equalization. If we have to go any faster, we will have to equalize the channel. So, the need for equalization becomes important. Let us look at an example. This is a simplistic example where we have only 3 received components. Most likely the first one is a line of sight and the next 2 are the reflected components. The first reflection is a stronger reflection, whereas the next one is a weaker reflection. On the x axis we have the tau in microsecond. This is an example. So, the first one tau 0 is labeled at 0, this is our starting ticker. Then at the first reflection comes at 2 microseconds after the first one and the next one at 4 microseconds after the first one. The relative strengths of the signals is different. So, these are, if we are talking about p of tau, is nothing but alpha 1 squared, alpha 2 squared and alpha 3 squared, the 3 channel gains. So, in this case, if you have to calculate the mean tau, it is given by the formula where you take p of tau 1 times the delay, p of tau 2 times the delay and p of tau 3 times the delay divided by the p tau 1 plus p tau 2 plus p tau 3, and if you calculate this value, it comes out to be 1.26 microseconds. On the other hand, if you have to calculate tau squared average, you plug in the formula and you get 3.79 microseconds squared. Okay? Very simplistic thing. In real life, you will not get 3 reflections, you will get many more, but here we are considering the 3 most significant reflections. The root mean square value sigma subscript tau from the formula under root tau squared average minus tau average squared from these two above values is 1.48 microsecond. So, for this simplistic value, the root mean square value is close to 1.5 microsecond. Now, if you continue with this example and ask the next question, if we want to employ BPSK, binary phase shift keying modulation, what is the maximum bit rate possible to send through this channel without the use of any channel equalizer? Okay. So, what is being sent is I am going to send a BPSK. So, maybe I will have a plus 1 value and a minus 1 value for every location, and when I send a signal, I get not 1 pulse, but 3 pulses. Clearly, this will cause inter-symbol interference. The question being asked is, given this scenario and no provision for an equalization, what is the maximum data rate that can be pumped? So, from one of our previous lectures, we have seen that the sigma tau over tau s, the symbol duration, should be less than 0.1, so that one of the signals does not interfere with the subsequent symbols, so as to avoid or reduce the effects of inter-symbol interference. From this equation, tau s, the symbol duration, should be greater than sigma tau over 0.1, but sigma tau in our case was 1.48 microseconds. So, here it is 14.8 microsecond. Rs, the bit rate, is nothing but 1 over Ts, approximately is equal to 67.5 kilobits per second. So, the actual limit imposed by this time dispersive channel is a maximum data rate of 67.5 kilobits per second. Clearly, there is a need for equalization. This kind of a data rate is not acceptable. Now, let us shift gear and talk about something different. We will talk about coherence bandwidth of the channel. A statistical measure of the range of frequencies over which the channel can be considered flat is the coherence bandwidth. So, it is again a statistical measure as the other time dispersive parameters we have talked about. What does it mean physically? It means that the channel passes all spectral components with equal gain and linear phase, as long as it is within the coherence bandwidth of the channel. So, it actually represents correlation between two fading signal envelopes at frequencies f1 and f2. So, in a very layman's language, if I send a signal at frequency f1 and I send a signal at frequency f2, if they fade in a correlated fashion, then they are within the coherence bandwidth. The maximum separation between f1 and f2, which will still give me correlated fading, will relate to the coherence bandwidth of the channel. Question?
So linear phase, it means that in the same direction the multipath component.
The question being asked is linear phase in the same direction of the multipath channel. Yes, linear phase is any standard definition of linear phase as you use in linear filters. Okay, the phase is not distorted. It does not give any phase change. It affects the phase of the all the frequency components. It is as if only a delay has taken place. Okay. It is not that the phase of the signal f1 is treated differently and distorted as opposed to phase f2. The phase shift provided for f1 is the same as that provided for the f2. An equal gain means that if I send signal f1 and it undergoes 10 dB of path loss or gain, f2 undergoes the same amount of gain. So, it does not distinguish between them. If f1 fades, f2 also fades, and vice versa. Okay. In fact, if f1 and f2 are beyond the coherence bandwidth, then if f1 fades, chances are that f2 will not fade, and this gives me a very simple fading countermeasure. It is called the frequency diversity technique. The coherence bandwidth, we will soon see, is a function of the RMS or the root mean square delay spread of the channel. The root mean square delay spread of the channel comes from the delay profile. The delay profile is obtained by measurement. So, all the measurement techniques are important because at the end of the day, those values will dictate the coherence bandwidth and the design of the frequency diversity schemes if we choose to deploy it. So, it is very important to carry out the delay profile measurements very carefully. Two frequencies that are larger than the coherence bandwidth. What is meant is the separation of two frequencies that is larger than the coherence bandwidth will fade independently. They do not undergo correlated fading. This concept is very useful for diversity reception, also can be used for diversity transmission. So, what is done is multiple copies of the same message are sent using different frequencies. How different are these frequencies? Separated by more than the coherence bandwidth. How do we get the coherence bandwidth? From the delay spread measurements. These frequencies are separated by more than the coherence bandwidth of the channel. So, coherence bandwidth indicates frequency selectivity during transmission. So, if my inherent bandwidth of my signal is larger than the coherence bandwidth of the channel, then automatically my signal can counteract or overcome the effects of fading. and that channel is termed as a frequency selective channel. So, let us give some quantitative face to the coherence bandwidth. If we define coherence bandwidth given by B subscript C as the range of frequencies over which the frequency correlation is 0.9. Clearly, within the coherence bandwidth, the signal undergoes correlated fading. The signal is correlated. So, if the correlation is above 0.9, that is a high degree of correlation, then B subscript C is given by 1 over 50 sigma tau. Sigma subscript tau, if you remember, is the root mean square delay. This is a very stringent definition. We can of course choose to relax the definition. If we define the coherence bandwidth as the range of frequencies over which the frequency correlation is above only 0.5, okay, then it is a much broader coherence bandwidth. BC is given by 1 over 5 sigma subscript tau. In literature, both are used, but to be on the safer side, we use BC as 1 over 5 sigma subscript tau. This is a more popular definition that is normally used. Let us look at an example. Let us say for a certain multipath channel, most likely an outdoor multipath channel, the sigma subscript tau is 1.37 microseconds. So, it is an outdoor channel measurement. I do my channel measurement, I obtain my power delay profile, I do my mathematics to find out the sigma subscript tau. It comes out to be 1.37 microseconds. We are interested in finding out the 50% coherence bandwidth for this channel. If we are to design a scheme which will overcome the effects of fading, we need to separate it by more than the coherence bandwidth. Let us use the definition B subscript C is equal to 1 over 5 sigma tau. In this case, if you plug in the value of sigma tau as 1.37 microsecond, the coherence bandwidth comes out to be 146 kilohertz. That is, if my signal being used over this channel is larger than 146 kilohertz, then automatically the fading effects can be overcome to some extent. Let us look at, for example, the old AMPS system which was deployed in the US. It is the analog mobile phone systems. Since the BC is greater than 30 kilohertz, which is the band typically used for AMPS, I do not need to use an equalizer for AMPS. Of course, AMPS is no longer being used, it is the previous generation. But if we are talking about GSM channel, which is 200 kilohertz per channel, then we definitely require an equalizer. Question?
So, further lower than the 50%,
Yeah.
the same equation should be used.
The question being asked is, for lower than the 50%, is there an equation? We defined for this 0.9 coherence correlation and then 0.5 correlation, which corresponds to the 50%. Typically, we do not go below 50%, because then you are really uncorrelated by definition. You are making the band larger and larger, and you are going into the domain. So, it is a much looser calculation. You will be wasteful in your calculation. Okay. If you are using frequency diversity, you need to have a larger bandwidth, but you should use only as much frequency separation as desired, because most likely you will be sending the same signal over the two frequency bands. Clearly, if you separate it too much, they will be uncorrelated. But the game is to find out the minimum separation required, and if you go below 50% to 20% or so, clearly the denominator will go down, the numerator will go up. So BC will become larger and larger. So it doesn't say much. Fine. So normally we will not go below this 50% definition. Let us look at another example. Our example where we had one line of sight and two reflected components obtained by measurement of the power delay profile. The first one comes at time t0 equal to 0, second one at 2 microseconds, and then at 4 microseconds. For this one, we had already calculated our sigma subscript tau to be 1.48 microsecond. We are interested in finding out for this channel alone, what is the coherence bandwidth? What should be the minimum separation between two frequencies transmitted over this multipath channel, which will fade independently? So again, let us use the 50% definition of the coherence bandwidth. BC is given by 1 over 5 sigma subscript tau, and if you plug in this value of sigma tau, you get 135 kilohertz. So if you transmit signal 1 at f1 and signal 2 at f1 plus 135 kilohertz, hopefully they will undergo uncorrelated fading. Now let us look at a slightly different topic, which is the coherence time issue and Doppler spread related to the coherence time. We are talking about the temporal nature of the channel. So far, delay spread, and which is clearly related to the coherence bandwidth, describe only the time dispersive nature of the multipath channel, that too in a local area. Clearly, many times we encounter mobile channels, or even if the transmitter and receiver are fixed relative to each other, we find that the channel itself is changing. We experience something called as a Doppler shift. That has to be factored into the equations. So the Doppler spread and the coherence time which is associated with the Doppler spread describes the time varying nature of the channel in a small scale region. It is usually caused by the relative motion of the transmitter and receiver. So let us capture this account. So brief look at the Doppler spread. We remember from our previous lecture that if the mobile station is moving with a certain velocity v, however a signal is impinged on the mobile station at an angle theta, then the FD, the Doppler frequency spread, is given by the velocity divided by the wavelength times cosine theta. Please remember, this lambda wavelength plays an important part. The Doppler spread BD is nothing but the maximum Doppler shift. Okay? So if the velocity goes up or down, wavelength is a whole range of wavelengths used for communication. We are only talking about the maximum Doppler shift. Clearly, the Doppler shift depends on the relative velocity of the receiver with respect to the transmitter and the wavelength of transmission. The theta, the angle at which the arriving signal reaches the receiver, also is important. So what does this Doppler spread BD do? It characterizes the frequency dispersiveness of the channel, as opposed to the time dispersiveness of the channel we talked about in the previous couple of slides. Or it talks about the spreading of the transmitted frequency due to different Doppler shifts. If we send a certain frequency, say a continuous wave, then at the receiver we receive a spread frequency. That is what is being characterized by the Doppler spread. It is talking about the frequency dispersiveness. It is obtained from the Doppler spectrum, indicates the range of frequencies over which the received Doppler spectrum is above a certain value. So I am trying to characterize and bring into the equations this maximum Doppler spread. So, what we have seen already is that the Doppler spread B of d is the maximum Doppler shift, and the Doppler shift f of d is velocity divided by wavelength times the cosine theta. If the baseband signal bandwidth is much greater than B of d, what is B of d? The maximum Doppler shift. In that case, the effects of the Doppler spread are negligible at the receiver. Okay. If such a case occurs, then this is a slow fading channel as opposed to a fast fading channel. So, it depends on the signal bandwidth. Let us now talk about the notion of a coherence time. Coherence time is a statistical measure. It is a statistical measure of the time duration over which the channel impulse response is essentially time invariant. If the symbol period of the baseband signal, which is the reciprocal of the baseband signal bandwidth approximately, is greater than the coherence time, we are talking about the symbol period and the coherence time. If the symbol period is greater than the coherence time of the channel, then the channel will change during the transmission of the signal. Hence, there will be distortions at the receiver. The coherence time T subscript C is defined as 1 over Fm, where Fm is the maximum frequency spread due to the Doppler shift and is earlier represented as B of t. So, it is a reciprocal of the Doppler spread. There are some popular thumb rules, because in the previous slide you saw that T of C is only approximately equal to 1 over F of m. M stands for the maximum frequency spread. The popular thumb rule is T of C is given by under root 9 over 16 pi Fm squared, which is nothing but 0.423 divided by F of m. F of m is the maximum Doppler spread. This is popularly used. The definition of coherence time implies that two signals arriving with a time separation greater than tau c are affected differently by the channel. If you remember, in the beginning of today's talk, we had projected one diagram which was a 2D mesh diagram. On one axis was the delay spread, on the other axis was the measurement taken at different times. So, this represents the second axis, where the signal, the channel changes with time. A large coherence time implies the channel changes slowly. Again, this is related to the Doppler shift. If you are moving very fast in a vehicle, your channel will change rapidly, and that will be a fast fading scenario. So, fast or slow depends on what is your symbol duration, whether the fading characteristic changes within a symbol interval, or the fade can be expected to be constant over several symbol intervals. That will decide whether it is a fast fading or a slow fading scenario. Our receiver systems in fading channels are designed taking into consideration whether the channel is slowly fading or is a fast fading channel, whether it is a frequency flat channel depending upon the coherence bandwidth, or the frequency selective channel. So, we have these four things that have to be considered before you start designing a wireless communication system. So, let us summarize today's lecture. We started off the lecture by talking about the time dispersion parameters. Specifically, we talked about the mean excess delay tau bar, the RMS delay spread sigma subscript tau, and the maximum excess delay, which is measured from the largest received signal strength, largest reflection, and x dB below that. What is the time spread for that? These help us to figure out the value of the coherence bandwidth of the channel. We learnt that two frequencies separated by more than the coherence bandwidth fade independently. Thus, it can be used as a countermeasure to overcome the effects of fading. Finally, we talked about coherence time, which is a measure of how fast the channel is changing. It is given by approximately the inverse of the maximum Doppler shift, and we realized that if we have to obtain time diversity, then we can send the same signal separated by the coherence time, and then we will have independent fades for the two signals sent separately temporally. Thus, we can use the coherence bandwidth and the coherence time to overcome the effects of fading if we understand how the channel treats the signals. We will conclude today's lecture here, and we will continue with some other channel parameters in the next lecture. Thank you.